Here's another problem dealing with inertia and energy. So you have a ball or a sphere throwing down an incline. We know that it is released, so there is no speed at the beginning, and it's rolling down the plane without slipping. Remember, without slipping is very important when there is both translation and rotational motion, because that's the only way to relate those two motions. If we don't know this information, then we have no clue what's the relation between them. So the first question is to determine the translational and rotational kinetic energy. So what do you do for that? Conservation of mechanical energy. At the beginning, there's no kinetical energy, it's at rest. So all the energy is potential, which is mgh. And at the end, there is no potential energy, because we suppose that here the potential energy is zero. That's why here the potential energy is mgh. So there's no potential energy, all the energy is kinetical. Translational kinetic energy, you all know, is 1/2 mv squared, I'm sure. And the rotation kinetic energy is 1/2 I, which is moment of inertia, times omega squared, which is velocity. It's the same thing basically, but inertia is like mass in a rotational motion. In a translational motion, the greater the mass, the harder to make it move. It's the same thing for rotation. The greater the inertia, the harder to make something rotate. And the angular velocity is the equivalent for the linear velocity. So it's basically the same thing. So we know I is 2mr squared over 5. And we go that angular velocity, we can write that as v over r. This can be any radius, and this velocity is the velocity equivalent to a point moving this radius away from the center of mass. So this is the circle, let's say. Alright, this is the center of mass. Let's say I suppose this is the point, then this is the radius, small r, and this is the velocity of this point, which is moving, the velocity of this point. This is so we can say that this velocity we're gonna choose to be the velocity at the edge, and I'm gonna say this is r, any r, any velocity, but we can choose any r and its equivalent velocity. So we are choosing the velocity at the edge. Its equivalent radius is the radius of the sphere, and which is equal to r. And we know that the velocity at the edge is equal to this velocity because it's rolling without slipping. Think about it. It makes absolute sense. If it's rolling without slipping, those two are equal. I can't explain it. You just have to think about it. So we can say that this is v over r. Alright, let me take everything here, shrink it down. So we can say that this is 1/2 mr squared, oh what the hell, mv squared plus 1/2. We know that I is 2mr squared over 5, 2mr squared over 5, and we know that omega squared is v squared over r squared. That's not square, so we can eliminate this and this, and we are left with mgh equal, we can factor out the 1/2 mv squared, and can eliminate those two, plus let me see, plus mv squared over 5. Right, so we can say that m2 mgh, basically here everything is algebra. We are interested in finding v squared, is mv squared plus mv squared over 5. So we can eliminate the m's, so we can say, I did something wrong. I can feel that I did something wrong. Where is my mistake? This is right. This is the inertia. This is the 1/2. Maybe I didn't. Oh, I factored the 1/2, so here you still have the 2. Excuse me. So you cannot eliminate those. You can, but I factored the 1/2. So here you have still a 2. So you have 7v squared over 5, 7mv squared over 5. And we said we can eliminate the m, so I'm writing the m. What's happening to me? So we can say that v squared is equal to 10 over 7 gh. I'm just gonna delete everything. Right, to this space. We said that v squared is 10 over 7 gh. We know that the kinetical energy, which is translational one, is equal to 1/2 mv squared. You just plug the v squared and you get 1/2 m 10 over 7 gh, which is, we can make this right to 5 over 7 gh. Therefore the kinetic energy, the rotational kinetic energy, you know that is mgh minus 5 over 7. Where's my m? And this is a capital M. Alright, mgh equal to 2 over 7 mgh. So this is the first part. Now we're gonna do the second part. So the second part, this we want its linear acceleration. We want the linear acceleration. For the linear acceleration, to solve it, you need the F equal ma equation. So I'm supposing that this is my x this is my x direction. This is x direction, and I don't, there is a frictional force, so I need my y direction too, and this is my y direction. So those two questions are the most interesting one. So what's the linear acceleration? We know that sum of the forces in the x direction is mg sine alpha At this level you should know that in the x direction and the way the gravitational force mg sine L theta at an angle. I'm not going into this every step to prove this. So it's mg sine alpha minus frictional force equal ma. And the second thing you know is the equation. Let's write the equation in the right direction. So we can say n minus mg cosine alpha is 0, but it's theta, but this one is not gonna help us. We need the torque equation too, and the torque equation is that sum of the torques, and in this case the only torque acting is the frictional force, because the normal force, it passes through the center, so doesn't make it rotate, and the weight acts at the center. So friction force is the only thing that has a lever arm and creates a torque causing a friction. So we can the friction sum of the torque, which is friction, equal to I alpha. Now we're gonna use the same logic and we're gonna say that alpha is equal to A over R. It's the same thing, it's the same way we prove that omega is equal to V over R. It comes from the concept that it's rolling down without slipping. Just think about it, I can explain it. So you plug this here, so you have the frictional force is I, which I'm gonna say is 2 mr squared over 5, and this is I over R. Alright, I'm gonna take everything here. No, that wasn't good. Write everything here, shrink it down, and I'm gonna plug this friction here, and everything is algebra after that. So mg sine alpha sine theta, this is theta, minus 2, said those two cancels out, 2 ma, and there is an r, over 5 equal ma. You can cancel the m's, and voila, you can have your acceleration from here, right? So we can say g sine alpha is equal to the acceleration, parentheses, one plus 2/5 r. Seriously, I don't need I don't think it depends. No. Did I do anything wrong? This is the acceleration. This is the frictional force. Oh, the torque is F times R. You see, my bad. So you have another R here. So yeah, so F, so this R goes with this R, and you have the friction to be 2/5. I'm making a lot of mistakes, but I'm not gonna redo the video because I'm not embarrassed of making mistakes, and it's better for you too. If I make mistakes, you can learn better. So 7/5 times acceleration equals g sine alpha. Therefore, the acceleration is basically 7g sine alpha over 5. and the magnitude of the frictional force acting on it. Alright, it's nothing. So we said that you just plug it in. I'm not gonna do it. You just plug this L acceleration right here and you solve for F. It doesn't help to understand the conceptual things, it's just algebra, so you can do it. It's very easy. So now here we have two interesting questions. They are conceptual questions. Now it's saying that the solid, alright, let me delete everything. I'll go to a new page. Alright. So the solid sphere is replacing by a hollow sphere of identical radius r and mass m. The hollow sphere, which is released from the same location as the solid sphere, rolls down the incline without slipping. What is the total kinetic energy of the hollow sphere at the bottom of the plane? Is the same thing. It doesn't make difference because mgh is the same thing at the beginning. The potential energy is equal to the kinetic energy, the total kinetic energy. What rotation at final? It's the same m, yes, it's the same g, I think so, and it's the same h, so it's the same, which is mgh. Alright, now state whether the rotation kinetic energy of the hollow sphere is greater than, less than, or equal to that of the solid sphere at the bottom of the plane. The rotational kinetic energy is greater because moment of inertia is greater. So more goes into this. So actually it reaches here, it takes a longer time to reach here because it has more rotation kinetic energy and less, therefore less translation kinetic energy. That's it.